Mixing is a fundamental process in various industries, including pharmaceuticals, food, chemicals, and materials processing. Different mixing mechanisms and principles are employed depending on the characteristics of the materials being mixed and the desired outcome. Here are various principles and mechanisms of mixing. Convective mixing. Convective mixing relies on the movement of materials within a mixing vessel due to mechanical agitation or fluid flow. This movement promotes the exchange of particles between different regions of the mixture, leading to uniform blending. Examples of convective mixing mechanisms include tumbling action. In tumbling mixers or blenders, particles move by tumbling action, ensuring thorough mixing. Agitation. Agitation by impellers, paddles, or blades creates fluid movement within the mixing vessel, facilitating mixing of ingredients. Diffusive mixing involves the random movement of particles driven by Brownian motion. This mechanism is predominant at smaller length scales and is essential for achieving molecular level mixing. Examples of diffusive mixing mechanisms include Brownian motion. Brownian motion causes particles in a fluid medium to undergo random motion, leading to their dispersion and eventual mixing. Shear mixing. Shear mixing involves the application of shear forces to materials to achieve mixing. This mechanism is particularly effective for viscous materials or materials with different viscosities. Examples of shear mixing mechanisms include high shear mixing. High shear mixers apply intense mechanical forces to materials, resulting in thorough blending and dispersion. Homogenization. Homogenizers utilize high-pressure or mechanical shearing forces to break down particles and create uniform mixtures. Fluidization. Fluidization occurs when solid particles are suspended and fluidized in a gas or liquid medium. This mechanism is commonly used in fluidized bed mixers and processes for granulation, coating, and drying processes. Cohesive mixing. Cohesive involves the adhesion and aggregation of particles due to intermolecular forces. This mechanism is important for cohesive materials that tend to stick together. Examples of cohesive mixing mechanisms include attrition. Attrition occurs when particles collide and break apart due to mechanical forces, promoting mixing and dispersion. Compression. Compression forces particles together, leading to their fusion and the formation of cohesive mixtures. Centrifugal mixing. Centrifugal mixing utilizes centrifugal forces to promote the mixing of materials. This mechanism is particularly effective for high-speed mixing and be used for various applications including emulsification and dispersion. Gravity mixing. Gravity mixing relies on the settling and stratification of materials within a mixing vessel. This mechanism is often used for blending materials with different densities or particle sizes. Ultrasonic mixing. Ultrasonic mixing utilizes ultrasonic waves to induce the mixing or dispersion of particles in a liquid medium. Ultrasonic waves create cavitation bubbles in the liquid, leading to intense agitation and mixing. Each of these mixing mechanisms and principles plays a crucial role in achieving a higher level of homogeneity, dispersion, and uniformity in the final product. The selection of a specific mixing mechanism depends on factors such as the properties of the materials being mixed, the desired outcome, and the scale of the mixing process. In the world of mixing, the types can be categorized based on the materials being mixed. Here's a breakdown of the common classifications. Solid-solid mixing. This is the most widely used type of mixing, especially in pharmaceuticals and food production. It involves blending dry ingredients like powders, for example, active pharmaceutical ingredients, APIs, excipients like fillers and binders in tablets, granules, small, uniform aggregates of powder particles, tablets, may need gentle mixing to avoid breakage. Liquid-liquid mixing. This type focuses on blending miscible liquids to create uniform solutions. Applications include dissolving APIs in solvents for further processing, mixing flavorings or syrups in beverages, preparing homogenized emulsions, mixtures of two immiscible liquids, like oil and water. Solid-liquid mixing. This method incorporates solid particles into a liquid phase to create suspensions or dispersions, preparing suspensions of antibiotics or anti-inflammatory drugs, incorporating flavoring powders into syrups, mixing pigments into paints. Gas-liquid mixing. This type involves dispersing a gas into a liquid to achieve various purposes. Examples include carbonating beverages by saturating water with CO2 gas, oxygenating water in aquariums or aquaculture systems, fermentation processes where yeast interact with sugars in a liquid medium. Gas-solid mixing. This mixing blends gas with solid particles, often used in pneumatic conveying systems where powders are transported using air pressure fluidization processes where gas flow suspends solid particles in a fluidized bed. The pharmaceutical mixing process is a fundamental step throughout various stages of drug development and manufacturing. It ensures the uniform distribution of ingredients, which is critical for achieving consistent drug delivery and therapeutic effect. Here's a breakdown of its applications and uses. For formulating drug products, solid dosage forms, tablets, capsules. Mixing is essential for blending active pharmaceutical ingredients, APIs, the medication itself. Excipients, inactive ingredients that serve various purposes like fillers. The dosage form. Binders, hold the ingredients together. Disintegrants, allow the tablet to break apart after ingestion. Lubricants, improve flowability during manufacturing. Liquid dosage forms, syrups, suspensions. Mixing is used to dissolve APIs in solvent, syrups, or other liquids. Create uniform suspensions by dispersing insoluble drugs or excipients. Pre-processing steps. Granulation, converting fine powders into uniform granules for improved flowability during capsule filling. Consistent tablet disintegration and drug release. High shear mixers are often used for this purpose. Wetting and dispersion. Mixing helps incorporate poorly soluble drugs into liquids, insoluble excipients to create uniform suspensions. Other applications. Ointments and creams. Mixing ensures the API is evenly distributed throughout the topical formulation. Sterile products, injectables. Aseptic mixing techniques are used within a controlled environment to prevent contamination in the final product. Research and development. Experiment with different formulations, various ingredients, compatibility and stability before large-scale production. Benefits of proper mixing. Dosage accuracy and consistency. Ensures each dose contains the correct amount of API for effective treatment. Product quality and stability. Creates a uniform product with consistent physical properties for optimal stability and shelf life. Process efficiency. Minimizes waste and improves mixing times. Improved drug delivery. Contributes to controlled release formulations or faster disintegration for better medication absorption. High shear mixers are workhorses in the pharmaceutical and food industries, used for creating emulsions, dispersions, and granulations. Working principle. Feeding. The liquid and solid components are introduced into the mixing chamber. High-speed impeller. A high-speed rotating impeller blade generates intense shear forces within the mixture. This impeller can have various designs depending on the specific application. Shearing action. The high speed and design of the impeller create several effects. Hydrodynamic shear. The liquid itself exerts a shearing force on the particles as they move around the impeller. Impeller particle interactions. The impeller blades directly impact and break down solid particles or droplets. Cavitation. The rapid movement creates areas of low pressure, causing bubbles to form and collapse. This collapse generates intense localized shock waves that further disrupt disperse particles. Homogenization. The combined effects of shear, impaction, and cavitation lead to the breaking down of lumps, dispersing solids into liquids, and creating fine and uniform emulsions. Advantages. Efficient mixing. High shear mixers achieve excellent mixing results in a short time. Fine dispersions. They can create very fine and uniform dispersions of solid particles and liquids. Emulsion formation. These mixers are highly effective in creating stable emulsions. Granulation. In wet mixing processes, high shear mixers can be used for granulation. Versatility. Different impeller design customization to accommodate various mixing needs. Disadvantages. High energy consumption. Heat generation. Due to the intense shear forces, friction can generate heat. Shear sensitivity. Some materials may be sensitive to high shear forces. Potential for particle degradation. There's a risk of breaking down particles excessively. Maintenance. High shear mixers have moving parts that require regular maintenance. Overall, high shear mixers are powerful tools for achieving efficient and thorough mixing in various pharmaceutical and food applications. However, the potential for heat generation, shear sensitivity, and energy consumption should be considered when choosing this method. Planetary mixers are versatile tools widely used in the food, pharmaceutical, and chemical industries for efficiently mixing a wide range of materials. Here's a breakdown of their working principle, advantages, and disadvantages. Working principle. Mixing vessel. The planetary mixer consists of a stationary bowl that holds the materials to be mixed. Planetary motion. A central shaft rotates the mixing arm, which carries an agitator blade. The key feature is the planetary motion, where the agitator blade not only rotates around its own axis but also revolves around the axis of the central shaft. This creates a complex mixing pattern that reaches all parts of the bowl. Scraper attachment. Many planetary mixers incorporate a scraper blade on the arm that continuously scrapes the sides and bottom of the bowl. This prevents material buildup and ensures all ingredients are incorporated into the mix. Speed control. The speed of the rotation and revolution can be adjusted to suit the specific mixing needs and material properties. Advantages. Highly efficient mixing. Minimal dead zones. The complex mixing pattern minimizes dead zones, leading to a more uniform final product. Versatility. A wide range of viscosities, powders, and thick pastes, making them suitable for various applications. Easy cleaning. Variable speed control. Disadvantages. Higher cost. Planetary mixers can be more expensive compared to simpler mixing equipment due to their complex design and functionality. Larger footprint. They may occupy more space compared to some other mixers. Potential for heat generation. High-speed mixing can generate heat, which might require cooling systems for temperature-sensitive materials. Noise level. Some planetary mixers can be quite noisy during operation. Maintenance. Maintenance of the moving parts is necessary to ensure optimal performance. Overall, planetary mixers offer a powerful and efficient solution for mixing diverse materials in various industries. However, their higher cost, larger footprint, and potential heat generation need to be considered when choosing the most suitable equipment for your specific need. Homogenizers are specialized equipment used to create extremely fine and uniform mixtures, particularly emulsions, mixtures of two immiscible liquids. Here's a breakdown of their working principle, advantages, and disadvantages. Working principle. High pressure pumping. The homogenizer utilizes a high-pressure pump to force the mixture through a narrow gap or valve, homogenizing valve, at high velocity. Shear forces. As the mixture passes through the narrow gap, it experiences intense shear forces due to the sudden change in pressure and high velocity. Cavitation. The rapid pressure drop within the valve can cause cavitation, the formation and collapse of tiny bubbles within the mixture. The collapse of these bubbles generates intense shock waves that further disrupt and disperse the particles. Homogenization. The combined effects of shear and cavitation effectively break down larger particles or droplet one liquid, for example, oil, and distribute them evenly throughout the other liquid, for example, water, creating a stable emulsion. Advantages. Ultrafine emulsions. Homogenizers can achieve exceptionally fine and uniform emulsions. Improved stability. By breaking down particles and preventing them from reaggregating, homogenizers create emulsions that are more resistant to separation and have a longer shelf life. Versatility. These mixers can handle a wide range of viscosities. Continuous processing. Homogenizers can be designed for continuous operation. Controllable process. Operating parameters like pressure and valve size can be adjusted to achieve the desired level of homogenization for different applications. Disadvantages: high energy consumption. The high-pressure operation requires significant energy input, which can be a cost consideration. Heat generation. Intense shear forces and friction. Homogenization can generate heat. Shear sensitivity. Some materials may be sensitive to high shear forces. Product loss. Depending on the homogenizer design, there may be some product loss during the process. Maintenance. Homogenizers have complex components that require regular maintenance. Overall, homogenizer mixers are valuable tools for creating ultrafine and stable emulsions in various industries, especially food and pharmaceuticals. However, the high energy consumption, potential for heat generation, and shear sensitivity of some materials need to be considered when choosing this technology. Ribbon blenders are workhorses in the pharmaceutical and food processing industries, known for their gentle yet efficient mixing of dry powders and granules. Here's a breakdown of their working principle, advantages, and disadvantages. Working principle: U-shaped trough. A ribbon blender features a horizontal, U-shaped trough made of stainless steel or other suitable materials. Helical ribbon agitator. Inside the trough, a helical ribbon agitator runs the entire length. This ribbon can have a single or double helix design. Mixing action. As the trough rotates, the ribbon agitator moves the material in a complex pattern. The outer portion of the ribbon moves the material from the ends towards the center, while the inner portion moves it back outwards. This folding and flowing motion gently blends the components throughout the vessel. Discharge. The mixed product is discharged through a port located at the bottom of the trough. Some designs may incorporate valves or butterfly closures for controlled discharge. Advantages: gentle mixing. The ribbon action provides a gentle mixing process. High efficiency. Despite the gentle action, ribbon blenders achieve excellent mixing uniformity. Versatility. They can handle a wide range of dry powders and granules with various densities and flow properties. Large capacity. Ribbon blenders come in various sizes, with some accommodating large batches of material. Low maintenance. The relatively simple design with minimal moving parts to lower maintenance requirements. Scalability. The design allows for easy scale-up from pilot to production volumes. Disadvantages: limited mixing intensity, suitable for applications requiring very high shear or intense dispersion. Dead zones. Careful attention to loading and filling techniques can help minimize this. Not ideal for liquids or pastes. Designed for dry materials and not effective for liquids or viscous pastes. Limited working volume. The working capacity is limited to around 50 to 70% of the total volume. Dust generation. During operation, some dust generation may occur, requiring dust control measures. Overall, ribbon blenders are a reliable and versatile choice for gentle yet efficient mixing of dry powders and granules in various industries. However, their limitations in terms of shear intensity, potential dead zones, and unsuitability for liquids or pastes should be considered when selecting the most suitable equipment for your specific mixing needs. The term cone blender mixture isn't entirely accurate. Cone blenders, also known as double cone blenders, are a specific type of mixer, not a mixture itself. They are widely used in the pharmaceutical and food industries for efficiently mixing dry powders and granules. Let's delve into their working principle, advantages, and disadvantages. Working principle: double cone design. A cone blender consists of two symmetrical cones positioned from base to base with a central axis. This design creates a tumbling action when rotated. Rotation: the blender rotates on the central axis, causing the material inside to cascade and tumble over itself. Mixing action: as the cones rotate, the material is lifted and then folds back down, repeatedly blending the components throughout the vessel. This gentle tumbling motion minimizes particle shearing. Discharge: the mixed product is discharged through a port located at the bottom of the blender. Some designs may incorporate butterfly valves for controlled discharge. Advantages: gentle mixing. The tumbling action provides a low shear mixing process, ideal for fragile materials. High efficiency. Cone blenders achieve excellent mixing uniformity within a relatively short time. Uniform discharge, minimizing product holdup in corners. Large capacity. Cone blenders come in various sizes, with some accommodating large batches of material. Easy cleaning. The smooth interior surface and minimal internal components facilitate easy cleaning. Scalability. The design allows for easy scale-up from pilot to production volumes. Low maintenance, lower maintenance requirements. Disadvantages: limited mixing intensity, not suitable for applications requiring very high shear or intense dispersion. Slower mixing compared to some blenders. While efficient, cone blenders might be slower. Potential for segregation, slight possibility of segregation. Not ideal for liquids or pastes. These blenders are primarily designed for dry materials. Overall, cone blenders are a reliable and versatile choice for gentle yet efficient mixing of dry, free-flowing powders and granules in various industries. The conical screw mixer, also known as an autumn mixer, is a versatile blender utilized in various industries for efficiently mixing dry powders, granules, and even some viscous materials. Working principle: conical vessel. The mixer features a conical-shaped vessel with a smooth, slanted bottom. This design promotes efficient material flow during mixing. Rotating screw. Inside the cone, a screw-shaped agitator rotates along a central axis. The screw can have different designs depending on the specific application. For example, ribbon-shaped for gentle mixing, paddles for more aggressive mixing. Mixing action. As the screw rotates, it pushes the material upwards along the slanted walls of the cone. Simultaneously, the material folds back down due to gravity and the cone's shape. This creates a three-way mixing action: axial movement, upward by the screw; radial movement, outward towards the cone walls; tangential movement, downward due to gravity and the cone shape. This combined motion effectively blends the components throughout the vessel. Discharge: the mixed product exits through a port located at the bottom of the cone. Advantages: versatile mixing. Conical screw mixers can handle a wide range of materials. Gentle mixing. The design allows for gentle mixing, making it suitable for fragile materials or those prone to shearing. High efficiency. Despite the gentle action, conical screw mixers achieve excellent mixing uniformity within a short time. Velocity. These blenders come in various sizes, with some accommodating large batch volumes. Space-saving design. The conical shape minimizes the footprint compared to some blenders with similar capacities. Uniform discharge, minimizing product holdup in corners. Easy cleaning. The smooth surfaces and minimal internal components facilitate cleaning and sanitation. Disadvantages: limited for highly cohesive materials, may not be ideal for very sticky. Batch process, not suitable for continuous production lines. Complex design, require more maintenance than simpler blenders. Potential for segregation, possibility of segregation. Uneven distribution, during mixing. Overall, conical screw mixers offer a valuable tool for efficient and versatile mixing of various materials in pharmaceutical, food, chemical, and other industries. Their ability to handle a wide range of materials with a gentle mixing action makes them a popular choice. However, limitations for highly cohesive materials, their batch process nature, and slightly complex design need to be considered when selecting the most suitable equipment for your specific need. Disclaimer: this channel does not promote or encourage any illegal activities, and all contents provided by this channel are meant for educational purposes only. Any copyrighted material on these slides is included as fair use for educational purposes only. It will be removed at the request of copyright owners.